For many years, let's say the technology was presented in an ASHRAE show in 2003. A lot of skepticism. People could not believe this is not going to work. This is too complicated. This is, let's say, it's going to be too expensive, or this is not possible. And let's say, very few people really believe in it. And let's say it was a tremendous effort from what I call the oil-free community. That's not just us, but our customers, technicians, engineers, consultants that really could see the future. And this kind of community worked very close to not just to prove this technology was the right one, but to make this today major mainstream for very, very large systems and what we call, let's say, high energy intensity buildings like data centers, hospitals, airports.
Well, hello, everyone. Thank you for joining Did You Know, the ESCO HVAC Podcast. So today we're spending time with Ricardo Schneider. How are you, sir?
I've been great, and you?
I'm doing well. We have an opportunity to dive into a compressor technology that many people are not very familiar with, especially in the residential and light commercial. Many technicians have seen that evolution from a reciprocating compressor into a scroll compressor and then into rotary compressor technology. But many don't even know what the Turbocor is. Can you give us a brief history of the development of the Turbocor?
Absolutely. So to get a picture about how the technology has been developing, we need to go back to the early 90s when the Protocol of Montreal was starting to be implemented with a very focus to phase out CFCs.
Yes.
So let's say this was related with, as people with my age can remember, the depletion of the ozone. And we started to see tremendous issues that was hurting, let's say, people, the planet, and a brilliant group of people in Australia was exposed directly to this problem because most of this ozone depletion was occurring on the Arctic or South Hemisphere. And these people start to think about what we need to do to resolve some of these major issues that our industry was creating. So a group of entrepreneurs and scientists got together and put this kind of a vision, a dream of a product that could address many issues that was kind of emerging at that time. One of them, as we said, to phase out the CFCs, to miniaturize centrifugal, because at that time centrifugals were kind of a very large machines and extremely expensive, and very few people knew how to manage this kind of technology. To integrate vapor speed technology at the same time, and make this a very smart compressor that could spin on and spin kind of in a different kind of RPM to provide the need for the load on cooling in the systems. And also they put this a very unique feature that should be frictionless, so no oil, because we all know that as part of this industry, oil is really a pain, because to bring the oil back to compressors, and sometimes they get let's say stuck on heat exchangers, on the piping, and you have to control the speed and do all the things that we need to do to bring the oil back. So this brilliant group of people put this kind of concept, and they started to brainstorm and put some prototypes. And the very first kind of a prototype was put in place in 1995 in Australia.
Yeah,
so that's kind of where the technology started,
Sure. Well, you bring up a very intriguing point with the oil. When we look at replacement refrigerants, right now we're going through our HFC phase down. And so whether you're in residential, light commercial, industrial, the entire industry is being affected by refrigerant phase downs, which means replacements. So like yourself, I've been in the refrigeration industry for a good portion of my career. And so I actually worked in that CFC phase out and the HCFC phase out. I worked with a variety of replacement refrigerants, and that was always a determining factor. What was the oil? What was the lubrication within my system to help determine what refrigerants I could use? Because a lot of people go, well, if we have a good refrigerant, Why can't we use it everywhere? We go, well, we have different oils and different applications. We were going from mineral oils and alkyl benzenes into polyesters and PVE oils as well. We primarily shifted to POE oil, but if we think about oil, oil is a restriction. It adds that extra viscosity. So we're putting weight on our centrifugals. If we could remove oil and we could allow the system to operate without oil, well, then our refrigerant selection becomes much wider.
Absolutely. And there's another element of eliminating oil. You're also eliminating a film that is covering all the heat exchangers, that is reducing the heat transfer capabilities of heat exchangers. If you look, let's say, in Shell tubes, a significant amount of oil concentration is deteriorating the performance of chillers, deteriorating performance of the heat transfer. So the oil is not just a problem to manage, but it is a factor that is degrading the efficiency of some key components.
Yeah, absolutely. So if we can eliminate the use of oil, we can eliminate twofold. So we can remove that, additional viscosity and slowing down of our flow. We can also increase the heat transfer. Sounds like a brilliant idea. Why don't we do it with every compressor?
Yeah, and there's some tricks in that. But another thing that I want to highlight it is once you eliminated this friction, why we need oil? Because we needed to reduce this metal-to-metal contact issues that we have with moving parts on the compressors and screws or pistons or rotary compressors. Once you eliminate the oil, there's another thing that is important, that you have a product like Danfoss Turbocor, that your performance is, let's say, maintained over time. You do not have efficiency degradation of the compressor over time. What it means, let's say that once a compressor is levitating this magnetic field with the magnetic bands, the performance of a new compressor or the performance of a 15 or 18-year-old compressor is the same.
Oh,
We have measured. So there's no degradation over time because there's no metal-to-metal contact.
sure. I mean, if we think about all of the friction points of a reciprocating compressor, we all love reciprocating compressors. They're just a tried and true piece of technology that they just run. They're very heavily built, but they wear significantly because we have continual wear of this cylinder through our pistons and our piston rings. We have wear on our bearings of the crank. We have wear at the bearings at the end of our motor casings. We have a lot of friction. We have valves that are moving regularly. So yeah, and as we transition, even our scroll compressors, yes, we may run on slightly less friction, but we still have a lot of friction within our scroll plates, within our bearings.
And the friction means, let's say, losses, because when you have, let's say, parts touching each other, you generate heat and you lose efficiency. So once you have an oil-free system, there is significant benefits from efficiency point of view, and from reliability and energy efficiency over time that is going to be guaranteed, basically.
Now, I would assume, not knowing from the engineering perspective, I would assume that as we machine the actual pump itself, our tolerances are probably very close on our mechanical pieces, but not to the point that they're actually wearing to each other. Is there any significant compression loss in that engineering aspect?
Yeah, that's a very good question. First, I needed to elaborate that we are using magnetic bands. It means, let's say, that you levitate the shaft. The shaft that is spinning about 48,000 to 45,000, 50,000 RPM. It's levitating on the magnetic field where there's no convex. The shaft and the bangs, they don't touch each other. So the compressor has a completely frictionless kind of setup, and we compress the gas through centrifugal technology. It means that we compress the gas through the speed of the impellers that are levitating attached to this shaft. So very different from a positive displacement machine like rolls or screws or piston. you compress the gas by speed. And that's kind of a very different principles of a compressor technology, because let's say you can really, let's say, reduce significantly the amount of parts. As you mentioned, let's say a piston compressor, you have a lot of parts, a lot of components that have to be lubricated. On the centrifugal machine, you have a shaft with impellers attached to the shaft. And it's spinning the very tight tolerances, actually, between the impellers and the volute to make sure that you don't have significant losses on the aerodynamic. So it's all combination of this magnetic bearing, centrifugal, and a very precise machining and a precise kind of combination of all these parts that's going to produce a high efficiency centrifugal machine.
So I would assume that a turbo core is designed on a horizontal axis so that the bearings are going to be on the ends so that it can maintain that shaft.
Correct. So it's all the configuration is horizontal. Then we have a configuration of compressors that have impellers in one side only, or we have configurations of a shaft with the impellers on both ends. Depending what is the kind of compression ratio that you're working with, you have to change the configuration of the compressor to make it more efficient and to make the compressor capable to reach high pressure ratio.
I see. So I would assume with no power being applied to the compressor, the shaft, is at rest, and then we energize magnetic windings at each end of the crankshaft?
Correct. So there is actually is two radial bearing and one axial bearing that is kind of levitating the shaft on the air. So that's another significant benefit, because a large machine like a screw machine, when you start, you have a tremendous inertia. Your amps go very high. Yeah. In our technology, you just need 2 amps to levitate the shaft, and then you start to spin. So you reduce tremendously the size of the electrical components or the power generation. If you have, let's say, like in data centers, a backup generator, so you can reduce significantly because you don't need all this peak current to select your components.
Absolutely. So when we look at the energy consumption, yes, we are going to apply current. We're going to apply a load onto our magnetic bearings, but it reduces that energy consumption overall. So pretty significant shift in technology.
Absolutely. For many years, let's say, when the technology was presented in an ASHRAE show in 2003, a lot of skepticism. People could not believe this is not going to work. This is too complicated. This is, let's say, is going to be too expensive, or this is not possible. And let's say, and very few people really believe in it. And let's say it was a tremendous effort from what I call the oil-free community. That's not just us, but our customers, technicians, engineers, consultants that really could see the future. And this kind of community worked very close to not just to prove this technology was the right one, but to make this today a major mainstream for very, very large systems and what you call, let's say, high energy intensity buildings like data centers, hospitals, airports.
Absolutely. So we can really look at the energy aspect of the turbocore compressor as being an energy efficient upgrade in compressor technology.
Absolutely. And a big part of the energy efficiency is coming from the integrated variable speed drive. So making the centrifugal machine move up and down the speed, that's how you gain efficiency. And let's say, and the compressor is so intelligent that they can run, let's say, multiple compressors on the same vessel, because there's no oil management required. Yeah. You can really kind of put 4, 5, 6 compressors on the same vessel and kind of play with the load of each one to make sure that we have a clear and a good match between the load and the capacity.
Wow. We're in an age of evolution in the HVAC industry. The refrigeration industry has been in a constant evolution. The HVAC industry has been a little dormant for a few decades. We've been stuck on the whole single speed and two stage compressors for a long time, and we're starting to move into variable capacity systems. And so, we have issues with some of our variable capacity because we're having to work with oil and oil return and many of these variable capacity residential light commercial systems. I can completely see the opportunity to replace our traditional thinking with variable speed compressors and start re-looking at oilless compressor technology. Is there a limit in capacity with the compressors, or has it just not been mainstream in our residential and light commercial sectors and air conditioning?
Yeah, you touch a very important point. Let's say the new technology is coming to our space.
Yes.
Another thing I think we needed to mention here is that, let's say, this compressor is basically a computer that's controlling the magnetic field, controlling the speed. And this computer today is connected to the cloud.
Oh, wow.
Tons of data go to the cloud to optimize performance, to use artificial intelligence to make things more intelligent, to kind of make the systems working better. And so this is kind of a renaissance of our industry, basically. That's what I call it. It's a very interesting. And how to make this scale up and scale down, it is a very different challenges. To make this technology going larger tonnage compressors, 400 ton, 600 ton, 1,000 ton, is relatively simple. To go down to light commercial and residential, this is very complex
Yeah.
because we have worked to miniaturize, make this a miniature of a centrifugal. Traditionally, the average centrifugal used to be 750 ton. Our smallest compressor is about 100 ton. So let's say to go to even smaller, the tolerances are becoming very challenging. So
Yeah.
we work with the 5 to 7 micron tolerances
Oh, wow.
in our design. And if you go to a smaller and smaller size, the losses are going to start to be bigger. So efficiency is going to be deteriorated, and the cost of manufacture is going to be high. So
Absolutely.
I think that we'll see this technology going smaller, but how far smaller we go, we still have to resolve a lot of problems.
Yeah, I can absolutely see that. Yeah, yeah. When you think about those tolerances, if they're critical on a 100-ton compressor, how critical are they on a 2-ton compressor?
We have been working on this smaller kind of platforms for years.
Mhm.
And I'm not saying that it's impossible, but it is a lot of big challenge that we still have to resolve. And eventually we'll get there. But it's going to be a big challenge for the whole industry.
Yeah, absolutely. Well, if we just think about, long term, as we start looking at ways to improve the technology of our equipment, ways to reduce our impact to the environment that we live in, if we can manufacture a system that does not use oil, so now we're not using, the oil refining, we're not using synthetic oils for every single installation, and we start looking long term, we start thinking, well, as machinery advances, as the demand advances, then we start looking at, well, down the road, this is practical in many applications. It would just take time before we get there. So I would imagine we would start seeing that compressor entering into markets going downward from that 100-ton capacity and working its way into smaller incremental compressors.
Yeah, and I think as the scale is growing, as more compressors are coming, and the cost is going to come down too, because let's say another element is the magnetic bands are still very expensive.
No, I
It's
bet.
still a very complex system. So if you look, let's say in residential, we have small scrolls, let's say with a variable speed, they are very efficient and they are very affordable. So to a technology like a Turbocor to replace a scroll, let's say, has to be even more efficient and at the same price. And this is the biggest challenge.
Absolutely. So where do you see the Turbocor going forward?
I think that this is just the beginning. So we see a tremendous demand for, as I said, high energy intensity buildings. So data centers today, it is one of our biggest market
Yes.
because let's say the energy consumption in data centers are so big, and the needed to meet reduced carbon footprint on these data centers are tremendous. So this is going to be the main growing demand for the next coming years for this technology. Another thing we have seen is heat pumps. So the decarbonization of heating to use electricity to replace, let's say, the traditional electrical heaters or replacing the natural gas boilers. So it is going extremely fast right now in Europe. So our volume in data center is growing extremely fast because we all know that, let's say, you can be extremely efficient in heat pump to generate hot water. And I think, let's say that it's much more efficient, and you do not depend from natural gas any longer, especially the folks in Europe that have been through this horrific situation with the war and the gas, natural gas coming from Russia. So
Absolutely.
they needed to move it to electrical source heating systems. And Turbocor is one of the ways to help them do this.
Yeah, I see that. We are very significant proponents of our decarbonization efforts. Just looking at it from a large perspective, we need to start focusing on our energy sources going forward, our renewable energy sources in particular. And so the move towards more electric options are really where a significant amount of our engineering and our science is going into. And when we look at utilities in particular, if we can utilize our high efficiency Turbocor compressors to produce, cooling and heating opportunities that are non-carbon based fuel,
Yeah.
then we can start looking at larger scale opportunities with heat pumps. And I absolutely see this being the future of most of our larger buildings, especially in new construction, looking at advanced heat pumps and the technology to reduce energy consumption. And that Turbocor is definitely a primary objective in that.
Another segment that is growing very fast is refrigeration.
Yes.
So our product, let's say, is capable today to be applied for ice rinks and to temperatures that are, let's say, suitable for significant part of the food and beverage processes. So we have seen adoption in brewery industries and carbon beverage industries,
Oh, yeah.
let's say food processes. So we don't go to a very low temperature like, let's say, frozen food, minus 40 Fahrenheit. That's not our target yet, but let's say we can go to a medium temperature application naturally. And it's a lot of applications right in the United States, in Europe, in Asia doing this.
Very, very interesting. Well, all right. Ricardo Schneider, president of the Turbocor Compressor Department of Danfoss. We are so grateful that you joined us today to talk about the evolution of compressors and the evolution of the Turbocor. What are ways that our audience can connect with Danfoss to learn more about your products and where our industry is going?
Yeah, if you go to danfoss.com, you can easily connect with the Danfoss Turbocor team to learn more about our technology. Or if you can search in the internet, and these days with artificial intelligence, you put there, let's say, what you want to know about Turbocor, and let's say you can get more information. And we are very excited. As I said, we are facing today, I think, a renaissance of our refrigeration air conditioning industry. So there's so many new technologies being adopted, so many things coming. That is fun again to be part of this industry. It's extremely exciting for the new generation to join us because this is a more digital kind of landscape. It's a lot of more innovation coming. So it is a fun time.
It absolutely is. I'm so grateful for this. We thank you for joining us, and we encourage you all to check out the Turbocor compressors at Danfoss. Have a good day, sir.
Thank you. Thank you for calling. Thank you back.